So let's continue a little bit. Random packing of bimodal. Previously, we were talking about mono size. Means every particle have the same size. Now we are talking about in system, we may have so-called different particle size distribution. And the simplest case would be called bimodal. Let's say I have spheres. One type of sphere is certain size. Another type of sphere are a different size, larger or smaller. And quite often people find if we have bimodal, even if they are each of the mode are mono-sized sphere, the overall I would reach a improved or higher relative packing density. Okay. And it's kind of, if you think about it, it's kind of from theoretical point of view, it kind of makes sense for larger particles. If I'm talking about larger particles, between them, I have what? Space, or so-called interstitial between large spheres, right? And then if I have smaller spheres, naturally that small spheres would what? Fill in the spaces between, or pores, also called interstitials, right? And naturally that would increase my relative packing density. Make sense? On the other hand, if we think, okay, let's start with small particles. Let's start with small particles. Small particles between them that are still so-called interstitials, right? But if we have larger particles, we are essentially, read to yourself, replacing the region of small particles with a lot of pores with a dense, large particles gives higher packing density. I'm showing something like this, right? Everything small particles. But let's imagine somewhere in the middle, I'm replacing that volume with a big solid sphere. Essentially, what happened? I'm eliminating or removing all the previous interstitial or pores or spaces between the particles. And as a result, this overall, I have a higher packing density. Make sense? Okay, very, very simple. Kind of like this connects to our day-to-day experience. The packing density for bimodal size spheres is a function of how dense can be packed. It's a function of ratio, the size ratio between the spheres. Make sense? The size ratio between the spheres. The extreme case is the other particle is just a similar size, slightly a niche, slightly smaller, but then I'm not getting much benefit. Make sense? You imagine the so-called smaller particle are just barely smaller than this. Then in that case, I'm not really taking any advantage of these two effects. Make sense? So the ratio definitely makes sense. The other one is fraction of the relative amount of the so-called larger particle versus the smaller particles. The relative fraction by weight or by volume, how much is larger particles? How much is smaller particle? And the other factor, as we mentioned, is the relative size ratio. What's the ratio in diameter or radius between the larger one versus the smaller one? And these two are independent or dependent? These two are independent, right? These two are independent. I can change different particle sizes. If I have the fixed particle size, I can change how much I'm mixing larger with the smaller. Make sense? These two factors are independent. Okay, so let's look at some actual data. For here, I'm showing the relative packing density versus the percentage of so-called coarse sphere in the mixture. So I'm still doing bimodal. I would have some on this side, everything would be larger or so-called the coarse spheres. Make sense? On left side, 100% coarse. On the right side, I have zero coarse, means I have 100% of so-called finer spheres. Make sense? And they follow different lines. Let's see, this is experiment. They are mixing 3.15 millimeter sphere, which they call core sphere. 3.15 millimeter core sphere with different so-called finer spheres. The finest one has 0.19 millimeter, whatever radius or diameter. The largest one 0.91, but all smaller than my so-called coarse particles. And then each of them I can change the relative amount between coarse versus finer. And what people observed is that, okay, for all these curves, roughly at around 73, something like this, 73%, I would have kind of the peak. Kind of it will somewhere in between for each of these pair of mixture, somewhere in between I would have reached a maximum. At the highest theoretical they can reach is roughly 86%. Highest, roughly 86%. And then you see that for the same ratio of coarse to fine, and the size ratio, right? This solid one is here. Open circle is here. And the size ratio getting larger and larger, which means the smaller compared with the larger one is getting smaller and smaller. I'm getting closer and closer to my 86%. Make sense? On the other hand, if my larger particle and the smallest particle are pretty much the same size, we would drop back to roughly 62, 63, which is the random packing for so-called mono-sized sphere. Remember here we are doing what? Ordered packing or random packing? Random packing, right? And the lowest you can get for so-called dense mono-sized is roughly 62, 63, something like that. And then when you start to mix larger with a smaller, the number goes up. Goes how much up? Depending on ratio between coarse and smaller. Also depends on the relative particle radius or diameter. And the larger the ratio, the higher this number be, but it cannot go to infinity. The highest in this bimodal is roughly 86%. Okay? And mathematically you can, if you want, you're curious, you can prove this. But not very complicated. Okay? And then let's look at a related plot. Here I'm also plotting packing density, relative packing density, still from 60 something, which is random mono-sized packing, up to bimodal highest 85, 86. Okay? And we are plotting versus particle size ratio. We're plotting particle size ratio. Okay? And we are mixing different diameters. We're using kind of different diameter. And for all of them, as the particle size ratio increases, the packing density increases. Probably here they are using roughly this 73 fixed amount between the coarse versus the finer. That's, I assume they're using this value, so that then they test the different particle size ratio and they see this increase, gradual increase. Okay, and here they listed a so-called triangle pore diameter. Triangle pore diameter. I'm plotting something like this. Do you see this is so-called triangle pore? right? Triangle. I'm talking about a space or gap or interstitials between three neighboring mono-sized sphere. And the largest particle that I can fit in here is mathematically you can calculate, right? By geometry, you can calculate this ratio. And that's roughly corresponds to here, with the size ratio roughly 6 something, okay? So that gives you an idea from, okay, ordered packing, mono-sized to, okay, mono-sized, random, and then to bimodal sized, but random, okay? And again, this gives you an idea what are the knobs you can play. You can play with the ratio between coarse particle versus fine particle. You can also play with the so-called particle diameter ratio or radius ratio, relative size.